Um, there was one question actually before I do that. Let me do an example problem that's related to this. It's sort of a cool question. The one in the practice problems, I think, is a mass, two masses connected over a pulley hanging from the ceiling of an elevator. And so the idea is, I think it should be in the kinematics, I think, particle kinematics. Oh, okay. Okay, no, you're right. Okay. Okay, so now particle kinetics. So kinematics is just describing the motion. So it's relationships between time, position, velocity, and acceleration. It's all things that, if you had a careful video of a motion, you could measure all this stuff off of the video. Kinetics is kinematics with causes of the motion added. So now we're going to start to include loads and mass properties. Since we're still talking about particles, there's no orientation. We're not dealing with object orientations at all. So the only loads or forces excuse me. And no couples. The only mass property we care about is the mass itself. There's no moment of inertia. And the only equation of motion is Newton's second law. So Newton's second law, I'm going to abbreviate that N2L. And Newton's second law says add up all the forces acting on an object. That's equal to the mass of the object times the acceleration of its center of mass. So this F net is the sum of all forces acting on the chosen object. Well, so that's sort of an interesting question. So let's think of an object as being a collection of all these particles bouncing around. Okay, and we're isolating the whole thing. Okay. So when we use Newton's second law, we just look for forces, external forces acting on this body. But the law itself says you have to add up all the forces acting on the body. That includes all the forces that are going on inside this boundary, which obviously creates a lot of problems because there can be a lot of complicated stuff going on internal to your boundary. The thing is, if you call this body 1, or this, particle 1 and this particle 2, the forces that they apply to each other are equal and opposite, and both of those two forces are included in the net force. And so all internal forces cancel out. They come in Newton's third law pairs. And so, yes, those are included in this net force, but we don't have to add them in because they cancel. The only things that don't cancel are the ones where something external applies a force to your object. Your object applies an equal and opposite force to the external, but you're not including forces on the external in your net force. Okay, so yeah, it does include those, but they all add up to 0. Anytime you use Newton's second law, and this also holds for the moment equation that we'll talk about with rigid bodies, you need to draw a free body diagram. And the free body diagram, the idea of that is that it gives you a list of all the forces that are going to appear on the left side of Newton's second law. All the loads that are going to appear in Newton's laws. So I want to start by giving some rules for free body diagrams. So the first thing is you need to draw a closed outline of the chosen body. And the reason it's important to draw a closed outline as opposed to like a stick figure or something is you're trying to be very clear to yourself and whoever's looking at it what forces are external and what forces are internal. So if your isolated object is a person, it should be something like that, not that. And the closed outline should have no internal details or external objects. So, for example, if you're isolating a car, okay, here's the outline. It should look like that. It shouldn't look like that. The window is an internal detail, the hubcaps or whatever. The grass is an external object. All that stuff is just confusing what you're trying to make a simple statement about what's inside your object and what's outside your object. Second, include all loads. And so here, I guess, is where I should say include all the external loads. You're not going to draw those internal loads. So include all external loads. That's forces. For now, it's only forces when we're dealing with particles. And couples also when we're dealing with rigid bodies. If a force direction is known, or I guess that's true of couples too somewhat. I'll just say forces. If the force direction is known, draw it as an arrow in the known direction. Associated with a scalar value or variable. So, for example, if you have a rope pulling on a car, the direction is parallel to the rope away from the chosen object, and you'd associate that with, well, if it's a rope, you'd do it with T. If the force direction is unknown, draw vectors in the coordinate axis directions and associate that with a vector value or variable. So in that case, like if we're talking about a friction contact between the wheel and the ground, those are the two vectors in the axis directions, and then you'd associate that with some vector. Now, a free body diagram has to account for every external force acting on the object. And actually, load is more general. Every external load acting on a chosen object. And so in really complicated problems, it can get sort of, you look at it and your brain can just sort of overload. Like there's a million things going on. How do you know when you've got them all, you know? And I think the best way to think about it is there are only two types of forces. Or let's say forces arise in only two ways. The first one is body forces. And those are primarily the weight. That's the one we're going to use all the time, but it also includes magnetic fields, electric fields. And once you've dealt with that, which is almost always just going to be the weight, the only other way forces arise is contact between the object's boundary and the outside world. So if you're systematic about this, it's sort of natural to look at complicated problems and sort of overload. But if you're systematic about it, you can, eliminate errors. Let me do sort of an example. All right, so let's say that there is, so this is like quicksand, and this is a Toyota Tacoma. And this is just a picture, not a free body diagram, so you can draw the external details there. Yeah, I'd recognize a Tacoma anywhere with those windows. And then in the back, there's a pig. Yeah.
Oh, that's its tail.
Yeah, that's its tail. No. Now you understand. Okay. He's going down. And then on the back of the pig is like one of those birds from the movie Up. And this guy is obviously distraught about all this going on, trying to push his Tacoma out of the mud. He's really upset. My bird! And I don't know, the owner of the quicksand wants this stuff to sink, so he's up in a helicopter trying to pull this guy away, pelting him with baseballs. Okay. So this is an example of a problem where there's a lot of stuff going on. Yeah. So let's draw a free body diagram of the truck. Well, in this problem, there's no mention of magnetic field or electric field. So the only field force, the only body force is the weight. So the truck coming from its center of mass just has a force vector acting down of mg. Now we're just going to mentally go around the boundary of the truck, looking for places where the outside world makes contact with the boundary. And that's all you have to do. So at the front, there's force quicksand. We don't know the direction, so I'm just going to leave that as let me just write out quicksand so that doesn't get confusing later. We don't, it would be in multiple directions. So for now, I'm just trying to go through and figure out what forces are applied, and we're not going to worry too much about directions. And now we're just going to keep going around the boundary. We get up here where he's pushing on the front. Maybe that's a force with a known direction. We can see he's pushing this way, so I'll call that R. I don't know. These are just variables. You can call them whatever you want. What about the winch and the helicopter, the lift from the blade of the helicopter, the force of the baseball hitting the guy? Yeah, right. That all comes indirectly through R. That doesn't show up in this free body diagram because it's not happening to the boundary of the truck. Okay? So we skip all that for now and keep going around. The next thing we have is the force applied to the truck by the pig. I'll call that force pig. And then what about the bird? Well, the bird's standing on the pig, so that will come into the problem indirectly, but in our free body diagram, this is all we need to represent. And now keep going around, you get back to the starting point of the boundary, and now we've treated the weight force, and we've gone around and represented everything that's touching the boundary of our isolated object, so we know we're done. And with all this stuff going on, we know that we're done with that free body diagram. So I would really recommend trying to be systematic about it. Do the weight force and then go around the boundary, and it makes it much easier to avoid mistakes. Now, what about free body diagram of the pig? Just to do one more of these. Curly tail. That's how you know it's a pig. Ooh, he's skinny. He looks like a cat. Okay, so there's the weight force. I'll call that. So this one up here, I'll call that mass of the truck times G. This one, mass of the pig times G. And now we'll go around the boundary. At the pig's feet, there's a force applied by the truck. And on the pig's back, there's a force applied by the, what was the bird's name up? Kevin? Okay. And now keep going around the boundary, you get back to the starting point, and so now we know we're done. Okay? Now there's a convention we're going to use when we talk about force vectors. I'm going to call it the double subscript notation. Just the same one we used in statics for the people who took statics with me. Double subscript notation for force vectors. And the key thing that can be a little confusing at first is we're going to use this notation for vectors. We're not going to use it for scalars that represent forces. Or not for scalar force variables. And this notation is, we're always going to write the force on one body by another body as the force something, something. And in this case, FAB means the force vector on body A by body B. And so if I redo the free body diagrams of the truck and the pig, so there's a weight force down. We know that direction, and that the magnitude is the mass of the truck times G. And now going around the boundary, there's a force on the truck by the quicksand. So I'm going to write that as, you can do it with a single letter representing it or whole words. I'm going to do on the truck by the quicksand. And then here, guys pushing the truck. Since we know the direction of that force, the variable associated with this force is a scalar. It's not a vector. And so I'm not going to use that double subscript notation here. I'm still just going to call that a variable r. And then keep going around, and you get to where the pig is sitting. That's an unknown direction, so I'm going to write that as the force on the truck by the pig. Now we're done with that free body diagram. And now if I redo the free body diagram of the pig, somehow he looks even more like a cat. Damn it. Because you can't see his nose. So there's a weight, mass of the pig times G. At the feet, there's a force with an unknown direction, force on the pig by the truck. And then up here, there's a force on the pig by Kevin. And the key thing with these redone free body diagrams is this force. There's this one pair of forces, the force on the truck by the pig, the free body diagram of the truck, and the force on the pig by the truck in the free body diagram of the pig. Where those subscripts are the same, they're just flipped. Okay. And in these cases where the subscript the subscripts are the same but switched, that's the type of force where Newton's third law applies. Yeah. So any questions about that subscript notation? Well, yeah, I'm going to talk about that. Yeah, at some point you'll have to do that. Doesn't matter to me on the free body diagram which one you do, but yeah, at some point in doing a problem you'll have to. Okay, so now Newton's third law. And I'm going to abbreviate this in 3L. This is the one that says for every action there's an equal and opposite reaction. And the meaning of that, I'm going to break it up into two ways of interpreting this mathematically. So there's two ways we're going to approach this in problems. The first one is in forces with known directions. So when you're dealing with forces with known directions, when you switch to the other contacting body, keep the variable the same, and switch the direction of the arrow. All right, so for example, if you have a body A in contact with a body B, then a free body diagram of A looks like this. The force B is, the body B is pushing on it, so I'll label it with a force with a known direction, variable R. And so then dealing with that contact force when you go to the other body, if I draw a free body diagram of body B, switch the direction of the arrow and keep the same label. A force with an unknown direction you just use the fact that the force vector on A by B is equal to negative force vector on B by A. That's where that double subscript notation comes in handy. That's the whole reason for it, is Newton's third law. So for example, if you have two bodies connected by a joint, I'll call this body 1 and this body 2. Then a free body diagram of body 1 looks like this. There's an unknown force a force with an unknown direction, F on 1 by 2. And then when you go to the second body, there's a force vector on 2 by 1. Since those subscripts are the same but switched, that's equal to negative F12. So recognizing that is going to be necessary for solving most of the problems in this class, because if you treat this as F12 and F21, those are two separate vector variables, 4 different variables that you need an equation for each to solve. If you recognize that this is just negative F12, you've cut down the number of variables by 2, and you only have a certain number of equations to work with, so that's going to be a key. Any questions about that?